Bismillahirrahmanirrahim. So this is the third lecture of chapter 1. In this lecture, we start with the algorithm. We have already seen the problem, the formulation of the problem formally in analytical way and graphical way. Then we have seen the method, Abou Kamel's method in detail. And then in the third section, we have seen how to apply it using the table. Now we will concentrate on how to implement it, to write an algorithm. So we are Saturday, الأحد 17 سبتمبر 23, Saturday 17 September 23 in Malaysia. So first thing first, what is an algorithm? So write it, introduction. We will define some concepts. Introduction. First of all, an algorithm. An algorithm is basically a flow or sequence of instructions. A flow of instructions. Each instruction is precise and has a specific task. So the instructions must be simple and precise. Let's symbolize this. This is an algorithm, general algorithm. Its task is to take an input our data, it processes them using its flow of instructions, and after processing, it gives us an output. The input is a set of variables, and the output also is a set of variables. Data input and data output. So there are two techniques to control this flow. The instructions are a sequence, but at some point you have to decide whether you repeat the instructions, the same instructions a couple of times, we call that a loop, or you have to decide which direction our flow will continue. So we have to choose a case among others. We call that conditional branching. Conditional branching. These are the two important techniques to control flow. So what is a loop? A loop is a block of instructions that you have to repeat several times. So repeat a block of instructions a number of times, a given number of times, until a condition, a Boolean condition, is satisfied. We call it the break condition. Until a break condition is satisfied. We will see that in when we implement the algorithm. We need first to give an overview of what is an algorithm, what you expect to find an algorithm, how to write an algorithm in general, and then we will write an algorithm for this method, for Abou Kamel's method. So these are general concepts. Now this is important particularly for those who have never studied computer science, programming, specifically. I've never programmed before. For those who knows, they know, of course, it is a loop and conditional branching. So a loop is a list or a sequence or a set or a block of instructions, of same instructions that are repeated several times until a given condition is no more satisfied, you break. Or is satisfied, you break, depending of your condition. So when your condition is a break condition, if it is true, you stop the loop. For conditional branching, you have to choose between several cases, between two cases or several cases. So you choose a case among others. If a condition is satisfied, I do this. Otherwise, I do that. Or you have several conditions. So in MATLAB, we will implement the algorithm in MATLAB. Some people use graphics, some charts. Some people use pseudocode that looks like Pascal or Fortran. But in this course, I use MATLAB. I use MATLAB to write the algorithm, and I use MATLAB to implement it. But here I will not go in detail, technical detail, how to write a function, how to write a script, how to compile the program. I will not do that. I just I focus on the algorithm, on the flow of the commands that I have to write in order to apply Abou Kamel's method. So I will use MATLAB. In MATLAB, to write a loop, there is two instructions, two keywords. There is a loop for. The loop for. You use a loop for when you have an index. And to control the loop, your loop, you use an index. Do this for the index equal 1, do then for equal 2, and until the index equal a given number. Then you use a loop for. We will not see that here in this. We will see that later in the practicals. We don't need loop for here, but it's important to know that there is two ways to write a loop. If you have an index, you use a loop for. If you have a condition, you use the loop while. Whiles mean while the condition, a given condition is satisfied, do the loop. Loop the instructions. Do the first iteration, the second iteration, and at each iteration, check the condition. If the condition is true, I continue, otherwise I break. So we have, and there is two ways to write the loop while. We will see that later. This is what we focus on in this section, because we will use it. And for conditional branching, MATLAB gives us also two instructions. If else, if a condition is satisfied, do it, do the instruction, or otherwise do the other instruction. Here you have to choose between two cases. But there are another scenario where you have several cases. You have to choose among several cases. Then MATLAB offers us the instruction switch case. Switch case, we will not use it here. We will use it in practical. As I have said in the first video, there will be a short series to introduce MATLAB. In that introduction, we will go in more detail and we'll show what is switch case and loop for. And we will repeat, also revise while. But here it's important to understand loop while and if else. It's very simple, very easy. You will see it's very simple, very easy. But when you study an algorithm, you have to know that there is two ways to control the flow of your instructions: a loop and conditional branching. And in MATLAB, we have two ways to express a loop loop for or loop while. And also two ways to express conditional branching, if else or switch case. So let's see two models of loop while. There is two models. Oh, see my notes. Loop while. Loop while. There is two ways to write or to express the loop while. The first is when we know a Boolean condition that control our loop. So we write while the Boolean condition means an expression that takes true or false, not a number. It's not a number here. It's not an arithmetic expression. It's a Boolean expression, either true or false. While this condition is true, execute the instructions here, whatever the instructions are. A block of instructions. When you have a sequence of instructions, we call that a block of instructions. So we have here a block of instructions. And we end the loop with end while. End while. The loop start here, executes the instructions, and it ends here. And while is optional. You can write just end in MATLAB or end while. But you need end. You start with while, you must finish your loop with end, so that the compiler software that reads, in our case MATLAB, knows where your loop starts and where it ends. And what is inside is called an iteration. This block of instructions is an iteration. So when the condition is true, the block is executed. This is the first iteration, and comes back. Is the condition still true? Yes. Then second iteration, and then third iteration, and at each time it checks the condition. When the condition is false, it jumps just after the loop while to execute the other instructions. So how it works, this is how it works, the first one. So this is the first one. Now this is the first one, model number one. This is when we know the condition for the first iteration. When we come to execute the first iteration, we know the value of the condition. In the second model, we don't know. In the second model, we don't know the value of the condition. So we write while true means loop indefinitely. And here we will have two blocks. Execute the first instructions, and in this first block we should evaluate our condition, our breaking condition. This is a block number one, the block number one of instructions. Then here we write if the condition, the break condition, here is called the break condition. Why? Because it will call an instruction called break. It will break, it will stop, while if condition is true, called break, and here we need and if. And you start with if, you end with and if. And this instruction is executed only if the condition is true. If it is not true, another block of instruction is executed. So your break condition can be at the end of the loop while or in the middle, but not at the beginning. At the beginning, it's the first move. So another block of instructions. Another block of instructions. Block number 2. This is block number 1, this is block number 2, and we finish the loop with and while. So the mechanics of this model, you will loop indefinitely until the condition becomes true. If the condition is true, you break. But when you come the first iteration, when you enter the loop while at the first iteration, you don't know the value of the condition. If you know the value, better use the first model. It's simple. In this section, we'll use this model, model number 2. I beg your pardon, model number 2. We will use this model. You will see why, because the condition is not known at, we have actually 2 break conditions. Are not known at the start of the loop. So this is the model of the loop while in MATLAB and in other languages also. Other languages has also do, until, etc. There are three ways to express a loop in other languages, but they are equivalent. So in MATLAB it's simpler. You have either for when you have an index, or while when you have a condition. You can write it this way or this way, depending of your knowledge on the condition, the Boolean condition. What is a Boolean condition? Okay, Boolean condition. Boolean condition. The Boolean condition is actually a comparison. You compare, you say, for example, x, is it equal? We use here 2 equals. When it's only 1 equal, it's an assignment. But when we use 2 equals, it's a comparison. This is a comparison. Is x equal to 0.5? It is either true or false. This is the Boolean condition. This is the condition, an example of a Boolean condition. It is a Boolean expression. While, for example, x plus 0.5, this is not a condition, this is a number. This is an arithmetic expression. An arithmetic expression. It's a number. They should not be here in the loop while or in if condition. Should not be here. Must be a Boolean expression. A Boolean expression can be true or false. We call that Boolean. That's why it's called Boolean expression. Another example, A different from B. Express different in this way. A different from B. It is either true or false. Or, for example, x minus y, the difference of x minus y is less than alpha, for example. It is also either true or false. X minus y is an expression, an arithmetic expression, is a number, and alpha, it is a number. And you compare them, you get either true or false, a Boolean expression. We can also combine Boolean expressions. We have, for example, 2, 3 more expressions. How we combine them? Using combine Boolean expression using and or. Means if this expression is true and the second is true, this is our new condition, or the first expression or the second expression, for example. But and or have different symbol in MATLAB and in C actually and C++. So we write, for example, we want to write A belonging to 0, 1. How we write that? How we write this? I write it in an expression to say that is A belonging to this interval or not? A Boolean expression. Is it true or false that A belongs to 0? How to write this? We write A is larger than or equal to 0. I'll use two symbols. Larger or equal to 0. Yeah, and it must be less than or equal 1. So we use and. Like this. This is the symbol for and. This means and. A less than or equal 1. This is our expression. It is a combination of two expressions. This is the first and this is the second. They must be both true, or otherwise the expression is false. Another example, x belongs to minus infinity, 1 not included, union 2 infinity. Means that x should not be between 1 and 2. It can be equal to, but it must not be equal 1. How we do that? We write x must be strictly below 1, smaller than 1. So this is the first instruction. And the second, it must be greater or equal to 2. So we write x greater or equal to 2. This is the second instruction. How we combine them? With or. This is or in MATLAB and in other languages. I remember 2 and n, not 1. 1 has another meaning. Use only one symbol has another meaning in binary. When we manipulate binary, but that's another topic. So when we manipulate a Boolean expression and we want to combine them using and, this is the symbol to use. And when we want to do combination with or, this is the symbol to use. So this is the first instruction, and the second instruction, it will give us the combined instruction of Boolean. So Boolean conditions that you find in the instruction while or the instruction if or while the condition must be a Boolean expression, true or false. To finish this introduction, let's see if. We have already seen here if. One instruction, it calls break. Has only one instruction, one single instruction. If the condition is true, you break. And you end your if with and if. Let's write it again here. 3, because we have also two models, if s. So in the first model, we have if condition. If the condition is true, execute one instruction. The block of our the block inside here or here can be one instruction, like here, one single instruction or several instructions. It doesn't matter. For that, a block of instruction. In the general case, it's a block of instruction. If it's one single instruction, you can also write it in one single line. like what we have done. So if the condition is true, execute this. But if it is false, never execute this. This is empty. So you come here to conditional branching tells us that we have a condition to satisfy. If it is true, we will execute, we will do some instructions. All the instructions here will be executed. Otherwise they will never be executed. There is another scenario, like this one, but a little bit different. If the Boolean condition is true, we will execute the block of instructions like here. But otherwise, if this condition is false, then execute another block. If you have two choices, then execute another block of instructions. And so if the condition is true, this is executed. This is executed only if the condition is true. Otherwise, the condition is false. This block is executed. So one single block will be executed. This one or this one, not both. But here, this block will be executed only in the case the condition is true. If the condition is false, there is no instructions to be executed. So you have two models depending on your algorithm. When you write 2 3, 4, 5 algorithms, you will get familiar to these two flow controls, loop while or if-else. And in the practicals, we will see the loop for and switch case. We have not seen here. We will see them later but here we need that. That's why I have done this small introduction, short introduction, I mean, to algorithms with MATLAB. Before to go to our algorithm, the final point is the zero, the abstract zero. So as you know, so let's write here number close to zero. As you know, irrational numbers and also rational numbers are expressed with a decimal point. For example, 2.312367, etc. In your brain you say etc. But in a machine, the number of digits that could be stored in memory are limited. So we have to make a decision. We have to make a decision to take only, for example, here we have 6 numbers. Our machine, for example, accepts only 7 digits, 7 significant digits. More than that, it will not. This will be not stored. And let's say, for example, here we have, for example, we have 3, 4, 5, 6. This will not be stored in memory. This is the first number. Let's call it alpha. And we have another number, beta. Exactly the same digit. The first digits are exactly the same. But the other digits are different. For example, here we have 9, 0, 1, 2, for example. So the question is, are these two numbers equal or different? They are, of course, different. Of course, in your brain, but in the machine, they are equal because the machine cannot see that, cannot store that, cannot manipulate that. And we call that round of error. Round of error means any number, so any real number, not integers. The integers, they call that. I used to call that integers. Integers like 1, 2, 3, etc., minus 1, minus 2. These are exactly stored in memory. But real numbers are stored always with a round of error, depending on the precision of your machine. So in MATLAB and Octave and in many other languages nowadays, in this recent decade, I think 20 years maybe, the machine generally use 16 digits. 16 digits to store a number. And we call that double precision number. Previously in the 70s and 80s, they used single precision number. They are still used nowadays for legacy only, for a legacy reason. So that old code will still work. But nowadays it is like ubiquitous. We work with 64 digits in binary to store 16 significant numbers. So what does that mean? What consequence has this on a number close to 0? So to say that alpha equals 0, another number alpha, call it a equals 0, how to express that in an algorithm? What is 0? So if you have 16 digits and there are still digits after 16, are they considered 0 or not? So let's take an example. We have here a equal plus minus, it can be positive or negative, and we have 0, 0, 0 till 0 here. And we have like 16 digits after 0. And still we have other number here, for example 1, 3, 7, for example, etc. Because a number can have an infinite sequence in mathematics, in abstract mathematics. In the machine, we cannot store this. This is the smallest number you could find. Plus 0, 0, 0, and here we have 2. So 0, the 16th digit is equal to, all the rest is 0. So this is the 16th digit after dot. And write this also, 2 times 10 minus 60. And in MATLAB it is called EPS, epsilon. EPS. So we can say confidently, if the absolute value of A is less than or equal EPS, then our A is equal to 0. Now in this case it is 0 because we will omit to compare the rest of the number. so they are not stored in memory. So we compare only that. If A, this is fs. The smallest number a machine can store, that is close to 0. Anything less than this number, it is a 0. So to express in an algorithm A equals 0, simply write it A, the absolute value of A is less than fs. So these are equivalent. And actually, we will not use LPS. We will use a number a little bit larger. So in our algorithm, we call that we are more conservative. In our algorithm, we use tolerance equal 100 times LPS. That is 0, 0, 0, 0, 2, 0 to 14 numbers. If you have 13 0 and then a number, it's a 0. We will not go to LPS because of a round of errors that could accumulate. You start with a precision of 16 digits, and after some calculation, the round of error will drop. The precision will drop. That's why, to be more conservative, we take our 0 to be to have 14 digits. 13 digits equal to 0, and the last one equal to. This is our tolerance. Any number in its absolute value less than the tolerance is a 0. Let's write it. This is number 6, I think. Let's turn the page. Now let's come back to Abou Kamel's method. What is the input? First thing first, the input and the output. What is the input? We said that an algorithm takes an input, process them, and give us the output. Before to see how they process the input and give us the output, what is the input? The input is, let me check here. So what is the input? The function that defines the equation, then the lower bound and the upper bound, xl and xu. We need also max EA. Max EA is the maximum error tolerated. When the approximative error that measures the progress of the XRI at each iteration, when it is less than its absolute value, less than max EA, we stop. So it's a bound for EA. Should be given as an input. And the tolerance. Any number in its absolute value less than tolerance is 0. So to say that A equals 0 means the absolute value of A is less than tolerance. So in practice, we choose max EA equal 0.05%. We choose it small. In the table with the pen and the calculator, we have chosen it 1%. But with the program, it's better to choose it smaller. And I usually choose it with this value to get a good precision. The tolerance, as I said, to be conservative, I choose it 100 LPS. That's it. 100 times the the smallest number in a machine. But I still prefer to give that as an input, because some users might decide not to choose 005, choose 01, for example, or much smaller 0001, for example. And same for tolerance. I have decided 100. Another colleague or student or research worker could decide. So it's better not to hard code it in the algorithm, but put it as an input in the interface of the algorithm. The input is the interface. Input output, as we will see later, is the interface of an algorithm. It's the first thing to decide before to design your algorithm. So this is the input. The function, the endpoints, and these two numbers, positive numbers, that will control the break, as we will see later, the break conditions. We use them in the break conditions. What is the output? The output is the solution XR at the ith iteration, and its image, and the error, the approximative relative error, the average at that iteration. And that's it. This is the input, and this is the output. The second thing, as you remember, the method is an iteration, and we have used a table, and we said that each row represents an iteration. So it's an iteration, it's a loop. But before to enter the loop, we need to initialize. Always in almost every algorithm, make sure before to write your loop, to initialize some variables. In the initialization, we need to initialize the image of XL. So we call F. This will execute F with the value of XL and give the image and store it in FX. And same for FU. F, XU, and semicolon. And then I will leave place here and come back, and you will see why. And then I start the iteration. I need the loop, so I write while. Do I know the condition? I don't know the condition. Not yet. So I use the second model while2. And I will write a large loop here. The first thing is to calculate XL. We have FL, FU, XL, XU. We apply the formula of Abou Kamel. XL equals FU multiplied by XL. Multiplication in MATLAB is done by star minus FL multiplied or times. Sometimes they call by, but normally we say times. FL times XU all over FU minus FL. All the variables are defined, are already defined. That's why we needed this initialization. But this is the current iteration, where we store the previous value, because we need the previous value. In the loop, we need XR I minus 1, the previous value, and the current value XRI, when we study the method. So XRI is XR. We cannot say to MATLAB XRI, it will not work. So is the variable XR, we named it XR. The previous value, we name it XR, the old value. And so before to write XR, we write XR, the old value. And we store in this value the previous value of XR. So before to calculate XR, we store the previous value, because it's an iteration. First times What is the value of XR the first time? We need to initialize it. Otherwise, what we put in XR RO? So we write here XR equals 0. We need this so that XR O equals 0 at the first iteration. Otherwise, the value of XRO will be undefined. So it's important to make this instruction. So that XR will contain 0. And then the new value of XR is this one. It was 0 and it becomes this one. And then we calculate FR. The image. We are following the table. XR. The table of Abou Kamel. Now this is the first thing to do in our loop. Then we check. We have said before that there are two break conditions. We check the value of FR equals 0. If FR equals 0, its absolute value, then we break, because this is the solution. So instead of writing FR equals 0, we write if the absolute value ABS is a function in MATLAB. ABS is a built-in means it comes with MATLAB, is a built-in function, and it means the absolute value. If ABS of FR that we just calculated is less than or equal to tolerance, then we can consider it as equal 0, and then we break. We are finished. We don't have to go. Of course, the first iteration, this will be false. And the second iteration, the old value of XR is stored, and then change here the new value, the current value. We get its image, and then we check. And it generates 2, 3, 4, the third or the fourth iteration. This will be true, and then we break. And so this is the first break condition. And this is a Boolean expression. It is either true or false. It's not, if you write only absolute value, this is a number. It's not a Boolean condition. It's a comparison. It must be a comparison to be a Boolean condition. Okay, a Boolean expression, I mean. And the second break condition is if is based on the error, on the error. But the error contains a denominator, which is XR, the current XR. So we must check first that XR is not equal to 0. So if ABS, the absolute value of XR, is larger than the tolerance, is not 0, then we can use the second breaking condition, which is based on EA. We know the formula. It's the current XR minus XRO over XR by 100%. This is ER we have seen before in this chart. But we used to note it XRI minus 1. And we said that XRO is XRI minus 1, the previous, and XR is the current. So you have to, because we divide, always when you divide in any expression, arithmetic expression, if you divide by a number, make sure it's different from 0, or its absolute value is larger than the tolerance, the current tolerance you are using in your algorithm. Otherwise, because there are cases where the XL is very close to 0. The solution is 0, and XL is very close. This could happen. Then this condition will not be used. This one will be used. And then, after calculating the expression VA, when it is defined, only when it is defined, in the majority of cases it is defined. Of course, XL is different from 0, but there are cases where, and we should take care about that, not neglect it, ignore it. So only when XL is different from 0, we calculate the expression, and then we apply the second break condition, the absolute value of EA, if it is smaller than or equal max EA, the bound, it is smaller than it. In the table, if you remember, it was 1%. Max EA, the given max EA, these are given as an input. If it is less than, then we break our loop, and always if you have if, finish it with and if. And this is the second break condition in our loop. And we write here and if. So this is the second part of instructions in our loop, but we have not finished the loop. We need the rule of signs. The rule of signs, as we have said before, if you have here XL, the current XL, and here you have the current XU, XL is somewhere here. This is our current XL. Same here, repeat it for the second case. XL, XU, XL. So we said before that we have two cases, at the left or at the right, the next interval. We have to decide which interval will be the next in our iteration. When we come to re-execute the block of instruction for the second iteration, we must before change our interval at the left or at the right. So what we do, if we are still in the loop while, if the sign is also a built-in function, and we have already said that it gives us 1 minus 1 or 0. So if the sign of FL is different like this, exclamation mark, and two operators, 2 marks, not mark, 2 operators, exclamation mark and equal, means different. For people who have never programmed or used MATLAB, because I have experience with students, they have no idea about programming, unfortunately. Anyway, if the sign of FL is different from the sign of FR, not U, FR, then it is at the left. At the left means this is our new endpoint. This will not change, and this will become our new endpoint. So the upper bound, XU, will become XL, and its image same, FL. Otherwise, if it is not the case, then it's at the right. And you see here we use the conditional branching. We have two cases to choose, left or right. If it is on the left, then do this block of instructions. Otherwise, the upper will not change, but the lower will change. So otherwise, XL become XL, and FL becomes FL. And this is the second block of the instructions if you are at the right. And we finish, of course, with and if. This is our instruction. And that's it. We finish our loop. And while. So we have first block, second block, and this is the third block. So I repeat again for pedagogical reasons. You have to iterate. Each iteration is the code of Abou Kamel or a row in the table we have seen before. So the first thing first is to store the old version, the old value of xn and calculate its new value, its current value, using the Abou Kamel formula. And then we calculate its image by calling the function that we have given as input. And this is the most expensive operation, is to call the function in our algorithm at each iteration. So we call, because the function can be complex, exponential, logarithmic, etc. All the rest formula are very simple. This is the most expensive operation in our iteration. Then comes to check whether we go to the next row, to the next port or not. We do two checks. The first is on the absolute value of fr. If it is close to 0, we break it. Otherwise, we use the formula of the error to check the progress of xr. xr minus the value, the previous value that we have stored in xr0 over xr by 100%. And we do that only under the condition that xr is not equal to 0 or is not close to 0. Otherwise, we get here infinity, get a number very, very large. So if our expression is okay, we check it. If it is under a given bound, then we break. So we have here checking whether we stop or not. And this is the second model of while, as we have shown it before. But here we have two instructions. You could have in other algorithm one instruction, one break condition, two or more, depending of the algorithm, depending of the problem the algorithm has to solve. And finally, we have to decide to go to the next row, to go to the next core, at the left or at the right. And as you see, very simple, no calculation, we just compare the signs. And if it is, we just change the value of the upper bound or the lower bound, depending on the place. And that's it for this lecture. Inshallah, we have another lecture, the last lecture, where we talk about the pros and the cons, special cases, and finally an overview of the other methods. I think a lecture should not exceed 1 hour, 40 minutes, 1 hour. That's why I subdivided it in 4 lectures. I have already posted 2 lectures. I will post this one, inshallah, today, Sunday, and I hope tomorrow, inshallah. I am a little bit late, but it's okay. Next week, inshallah, we will be ready to do our tutorials. So I post all the lectures before doing tutorials. And the week after, we will do practicals. We will come back to our algorithm with software Octave, and I show you that. So, inshallah, tomorrow the last lecture for this chapter, and next week the tutorials. See you then later, and peace.